Welcome back to our physics class. Today we are going to deal with reciprocity theorem and star delta transformation. First we will go to reciprocity theorem. So what is reciprocity theorem? And the statement is, in any linear bilateral network, if a source of EMF E in any branch produces a current I in any other branch, then the same EMF E acting in second branch would produce the same current I in the first branch. So that is the statement of reciprocity theorem. And it simply states that we can interchange both EMF E and current in any branch. We can interchange E and I. So the theorem simply means that E and I are mutually transferable. So a current source causing a voltage V at any node can be moved to another location and it will produce the same voltage V in the circuit. So that is the simple form of reciprocity theorem. We can move on to this theorem in detail. So this reciprocity theorem is applicable only to single source networks, so that it cannot be employed in the analysis of multi-source networks. Again, the theorem states the following: the current I in any branch of the network due to a single voltage source E will equal the current through the branch in which the source was originally located if the source is placed in the branch in which the current I was originally measured. It simply means that, the statement simply means that the location of the voltage source and the resulting current may be interchanged or can be interchanged without a change in current. That means in a circuit we are having a single source, and that voltage source and the current in any branch can be interchanged so that there will not be any change in current. See, this is the first figure. Here you can see that there is a current I here due to the voltage source E, and in the reciprocity theorem states that we can interchange this current and EMF so that there will not be any change in the network. So in the second figure you can see that the current is here and the EMF is here. So if the position of the current and EMF is interchanged, the current will be the same in both the circuits. So that states the reciprocity theorem, and we can move on to the proof. So we will analyze first the first figure A, figure 1A, then we will analyze the second figure, whether the reciprocity theorem stated is correct or not. For that, we are taking this circuit and the resistances values are given. See, R1 is 12 ohm, R2 is 6 ohm, R3 2 ohm and R4 4 ohm. And the source of EMF here is 45 volt. And you can see that the current flowing through the circuit is IS. And here you can check for another current the current in another branch, and that current is given as I. Now we are going to calculate the value of this current. So for that, in order to get the current in the circuit, we need to know whole current in the circuit. We need to know the total resistance of the circuit, isn't it? So you can see that R1 and R2 are in series. Similarly, R3 and R4 are in series. But these resistances are in parallel. That is, R1 and R2 are parallel to R3 and R4. So you can calculate the total resistance. R1 plus R2 parallel R3 plus R4. So that gives you the total value of resistance as 15 ohm. You know how to calculate the effective resistance when they are connected in series as well as parallel. So from that you can calculate the total resistance as 15 ohm. Now the total current IS flowing in the circuit is given by V by R. Now the voltage is 45 volt and the total resistance obtained is 15 ohm. So 45 by 15 giving you 3 ampere. So 3 ampere is the IS, that is the current flowing through this circuit. Now you can see that when this IS flows through this and reaches the junction, it gets separated into 2. So that means I is IS by 2. So 3 divided by 2, that is 1.5 ampere. So we got the current I as 1.5 ampere. Now what we are doing? We are checking for the reciprocity theorem, isn't it? So we are interchanging this E and I and are again checking whether the current is 1.5 ampere or not. So in the second figure you can see that the EMF, the source of EMF is moved to this portion and the current I is moved to here. So now we can calculate again the total resistance RT as R4 plus R3, that is the series resistance which is in parallel with again the series resistance R1 and R2. So R4 plus R3 plus R1 parallel R2. So that gives you the total resistance as 10 ohm. Again now we are going to calculate the total current in the circuit, that is IS. Again voltage by current 45 by 10, that gives you 4.5 ampere. Now that current is flowing here and it gets splitted into this and this, that is the current. Now we are going to find out what is the current through this resistor R2. So current through this resistor can be found out by Ohm's law, V by R. Now what is the voltage across this resistance R2? Voltage across this is current into resistance. So the current we got it as 4.5 ampere into 6 ohm divided by the total resistance in the circuit is 12 plus 6. So 12 plus 6. So that again you got the answer as 1.5 ampere. So what does it mean? Even though we have changed the EMF and current in any branch, there is no change in the current, isn't it? So that is the reciprocity theorem, which states that if a source of EMF in any branch produces a current I in any other branch, then the same EMF in the second branch would produce the same current I in the first branch. That means that E and I are mutually transferable and the ratio E by I is known as transfer resistance. We know that V by I is R, isn't it? So here E by I is known as the transfer resistance. So that's about the reciprocity theorem. Now we can move on to our circuit transformation. Why we are using this circuit transformations? To make the calculations easier. So here there are two types of transformations are there: delta to star connection as well as star to delta connection. So two type of transformations, delta to star connection and vice versa. See here R1, R2 and R3 are connected along the sides of a triangle. So that forms the delta circuit, whereas RA, RB and RC, these three resistances can be connected to a common point and that forms the star connection. So why we are doing this transformations is that we can make the complex networks simple and we can solve them. So for that we are using these star delta transformations, which are also known as T-pi transformation. So the first figure shows the delta connection, in which you can see that R1, R2 and R3 are the three resistance which is connected in a delta structure, isn't it? In delta format between the terminals A, B and C. So that is the delta connection, and in the second picture these three resistances are connected, replaced by these three resistance R1, R2, R3 are replaced with three resistance RA, RB, RC, and they are connected in a like a star with the terminals A, B and C. And the peculiarity of this star and delta arrangement is that these two arrangements will be electrically equivalent if the resistance as measured between any pair of terminals is the same in both the arrangements. So we can make a delta into star connection as well as a star into delta connection. Okay, so we are here for the first transformation, that is delta into star transformation. So here we are having this delta connection and also the star connection. See, we are going to measure the resistance between the points A and B in delta connection. So what is the total resistance? R2 and R3 are in series and it is in parallel with R1. So that is the total resistance between the points A and B in a delta connection. So R1 parallel R2 plus R3. Now, since we know that these two systems are identical. So since the two systems are identical, the resistance measured between terminals A and B in both the systems must be equal, so that we can write it as RA plus RB, which is equal to, that means the resistance between the terminals A and B, RA plus RB will give you R1 into R2 plus R3 divided by R1 plus R2 plus R3. That is what we had said earlier. That is R1 in parallel to R2 and R3 will give you what? R1 into R2 plus R3 divided by R1 plus R2 plus R3. That is the total resistance between the points A and B. Similarly, you can calculate the total resistance between B and C. What is that? RB plus RC. Again, you can calculate the effective resistance and also the resistance between the points C and A, that is RA and RC. The total resistance will be RC plus RA, that is equal to R3 into R1 plus R2 divided by R1 plus R2 plus R3. So you got three equations by analyzing the resistance between the points A and B, B and C, and C and A. What you have to know is you have to check which all resistance are connected in series and which all resistance are connected in parallel. By analyzing three terminals, you got the total resistance as RA plus RB, RB plus RC and RC plus RA. So you got three equations. Now you multiply these three equations, what you will get? 2 into RA plus RB plus RC. From that you can get the total resistance, that is RA plus RB plus RC. Now you can subtract 1, 2 and 3 equations from this fourth equation and you can have the values of RA, RB and RC. See, we had started from delta connection, isn't it? Isn't it? So delta connection means it is having resistance R1, R2 and R3. Now you can make this delta connection a star connections with resistance RA, RB and RC. So what is the value of RA, RB and RC in a star connection? That is what we had obtained through these equations. That is RA, RB and RC from R1, R2 and R3. So if you are having a delta connections with resistances R1, R2, R3, that connection is equivalent to a star connection with resistance RA, RB and RC with the given values of RA and RB and RC as this 5th, 6th and 7th equation. So that is the delta to star transformation. So for delta or delta bar star transformation, the resistance of each arm, that is RA, RB and RC of the star, we know that RA, RB, RC are the resistances in the star connection, isn't it? So the resistance of each arm of the star is given by the product of the resistances of the two delta sides that meet at its end. That means RA is obtained with the product of R1 and R3, RB is obtained with the product of R1 and R2, RC is obtained with the product of R2 and R3, divided by the sum of the three delta resistances. So we got RA and RB and RC with the help of R1, R2 and R3. I repeat, for delta star transformation, resistance of each arm of the star is given by the product of the resistance of the two delta sides that meet at its end divided by the sum of the three delta resistances. So that is the delta to star transformation. Now we can move on to see what happens when if all the resistances are equal. If R1, R2 and R3 are equal, you can again simplify this equation, isn't it? So if R1 equal to R2 is equal to R3 is equal to R, what will be RA? RA will be R square by 3R, that is R by 3. RB will be R by 3, RC will be R by 3. So that is given in the, if the delta connected system has same resistance R at its three sides, then equivalent star resistance will be R by 3. Clear? Now we can move on to star delta transformation. So already we have with us 7 equations. Now we can do some sort of simplifications and can find out how we can transform from star to delta connection. So what we are doing is we are multiplying 5th and 6th equation, 6th and 7th equation, also 7th and 5th equation. So 3 multiplications are done and all these 3 equations are added. That is 5 into 6th, 5th into 6th equation plus 6th into 7th equation plus 7th into 5th equation is done and we got this long equation. And again simplifying, what you will get, RA, RB plus RB, RC plus RC, RA is equal to R1, R2, R3 divided by R1 plus R2 plus R3. See in the first step you can take R1, R2, R3 outside. So the bracket will be R1 plus R2 plus R3, which is cancelled with the denominator. So the final equation is R1, R2, R3 divided by R1 plus R2 plus R3. That is the 8th equation. Now one more step. Now dividing the 8th equation with the 5th, 6th and 7th equation, you can do it by yourself. It's simple. So that we are having 5th, 6th and 7th equations in the previous slide, and you multiply, you have to divide the 8th equation with the 5th, 6th and 7th equation. Then what you will get? You will get R1, R2, R3 as R3 as RA, RB plus RB, RC plus RC, RA by RA. You can simplify it again. See, denominator you have RA, isn't it? In the numerator, in the second 2 terms of the numerator there is RA. So RA get cancelled. So what it will be? RC plus RB plus RB/RC by RA. Similarly, R1 and R2 can also be simplified. So, in star to delta transformations, we have the resistance RA, RB and RC in star transformation. So, this star transformation, star connection can be converted into delta connection with the resistance R1 and R1, R2 and R3 given by these equations. So, for star delta transformation, equivalent delta resistance, see these are the delta resistance, R1, R2, R3 are the delta resistance, is given by the sum of star resistances between those terminals plus the product of star resistance divided by the third star resistance. That means for R1 it will be RA plus RC plus RC RA by RB. Similarly, you can get all the three equations. So that's about the topic reciprocity theorem, delta star transformation and star delta transformation. Okay. Thank you.